Good evening, and welcome to Public Observatory Night, hosted by the Center for Astrophysics, Harvard and Smithsonian. I'm your host, Nadia Whitehead, and a public affairs officer here at the CFA. Tonight, we're pleased to present the lecture, All That Glitters is Gold, in a virtual format, live streaming to both our Facebook and YouTube channels. We'll have time for questions at the end of today's lecture, but if you would like to ask something during the presentation, simply type it into the comment section of our Facebook or YouTube stream. We'll answer as many questions as possible at the end of the talk. If you're interested in receiving our e-newsletter and information about future observatory nights or other upcoming events, please make sure to sign up for our mailing list by visiting the link that's appearing on the screen now and in the comments section. Now, I'm pleased to present tonight's extraordinary guest speaker, Dr. Edo Berger, who will present on the cosmic origin of gold. Edo Berger is a professor of astronomy at Harvard University who studies a wide range of astrophysical explosions and high-energy phenomena, such as supernova or exploding stars, tidal disruption events, where a star is torn apart by a black hole, and gravitational wave events. This work is based on observations across the electromagnetic spectrum, from radio to gamma rays, using ground-based observatories around the world and in space, as well as machine learning and artificial intelligence approaches. Edo holds a bachelor's degree in astrophysics from the University of California, Los Angeles, and master's and doctoral degrees in the same field from Caltech. After earning his PhD, Edo received a joint NASA Hubble Fellowship and Carnegie Princeton Fellowship to conduct postdoctoral research at the Carnegie Observatories and Princeton University. In addition to serving as a professor at Harvard, Edo is a science advisor at the Radcliffe Institute for Advanced Study. Now, please join me in welcoming Edo Berger. Edo, thanks so much for taking time to present to us tonight. I'll let you take it away.
Thank you very much, Nadia. Good evening, everyone, and thank you for joining me today to hear about exciting results from the universe. Today, I'm excited to share with you a story, a detective story, about the cosmic origins of gold. In particular, how on August 17, 2017, our research team used information carried by light, the traditional way of studying the universe, to discover gold and other rare heavy elements whose cosmic origin has been a complete mystery up to that point, being forged in a powerful collision between neutron stars, seen for the first time through the emission of gravitational waves, a brand new way of sensing the universe. My goal for the next 40 minutes is to explain this very long sentence and to take you through the scientific and personal story of this discovery. But before I do that, I want to highlight that this was a truly unusual scientific discovery, both in terms of its scope and the fact that it can be traced to a specific event, to a specific moment in time. As scientists, if we're lucky, we achieve a single scientific breakthrough at a time. But in this case, there was an unparalleled series of firsts. The first detection of gravitational waves from colliding neutron stars, the first joint study of gravitational waves and light, the first evidence for the synthesis of heavy elements, and the first time that the fields of general relativity, nuclear physics, high-energy astrophysics, and cosmology were combined in a single study. But to set the stage, we first have to go back an entire century. The year is 1916, and Albert Einstein publishes a revolutionary new theory of gravity called the General Theory of Relativity, or GR. GR posits that the gravitational attraction between objects is due to the curvature of space-time caused by their mass. The more massive an object, the more it curves space around itself, and hence, the stronger its gravitational attraction. The famous physicist John Wheeler explained this elegantly, saying, matter tells spacetime how to curve, and spacetime tells matter how to move. So according to GR, the Earth orbits around the sun not because of some unseen force between them, but because the sun curves the space around itself, and the Earth is forced to move in orbit within this curved space. A key prediction of Einstein's general relativity is the existence of gravitational waves, ripples in space-time caused by the acceleration of mass, For example, when two objects orbit each other in a binary system, as you can see here in this image. In some sense, you can think of these gravitational waves as analogous to ripples on a pond when you throw in a rock. Now, Einstein himself had a really fraught relationship with gravitational waves. In 1916, he stated very clearly, there are no gravitational waves analogous to light waves. In 1918, on the other hand, he revisited the issue and provided the basic formulation for how we think about gravitational waves today. But then in 1936, he again published a paper casting doubt on the existence of gravitational waves. In a sense, Einstein did what every good theoretician does. He hedged his bets. This way, whatever the outcome, he could claim credit for the discovery. It was only after Einstein's death that several independent efforts in the 1950s and 60s finally established that gravitational waves should indeed exist. These theoretical studies argued that gravitational waves carry away energy, causing these binary systems to spiral in and eventually collide, as shown in this computer simulation of two merging objects. You can see the gravitational waves emanating from the system, causing the orbit to shrink until the two objects merge into one with a final burst of gravitational waves. Once the objects have merged, the emission of gravitational waves stops. Therefore, the amplitude and wavelength of the gravitational waves carry information about the objects generating them. So if we could measure gravitational waves, we could determine the masses, distances, spins, and other parameters of the objects that are producing those waves. Information that may not be accessible to us in any other way. In actuality, this analogy of ripples on a pond only goes so far. Gravitational waves are in fact a compression and stretching of the curvature of spacetime itself, propagating at the speed of light, as shown in this animation. For example, if we formed a circular ring of free-floating particles, the passage of gravitational waves through the ring would first compress the ring along one axis and then the other. This stretching and squeezing effect is a unique signature of gravitational waves. As a result of this stretching and squeezing effect, here is a vastly exaggerated view of what happens to objects on Earth as gravitational waves pass through them. You can see the Earth stretching, squeezing more and more as the gravitational waves pass through. Now, this happens all the time. Even as you are sitting at home right now listening to this talk, gravitational waves from outer space are passing through the Earth, stretching and squeezing it. The strength of a gravitational wave signal is given by something called the strain, the change in length of an object relative to its length at rest, as gravitational waves pass through it. For example, in this case, the ring deforms from its undisturbed circular shape by about its full radius, so the strain is about 1. In general relativity, Einstein tells us that the strain is given by the following equation. Now, don't worry, this is the only equation in the talk, and I can promise you that there is no test at the end of this lecture. What you really need to know looking at this equation is that g, Newton's constant, is a very small number. C, the speed of light, is a very large number, and we take it to the 4th power. D is the distance, which for astronomical objects is astronomical. So this quantity, g divided by c to the 4th power divided by d, is an incredibly small number. Therefore, our only hope of detecting gravitational waves is to look for sources that produce an enormous energy in gravitational wave to compensate for this small number. This requires incredibly massive and dense objects. Even so, this effect is unbelievably small. It is about 1 part in 10 to the power 21. So what are these dense objects that can produce large energy in gravitational waves? The densest, most massive objects in the universe are neutron stars and black holes, the remnants of powerful supernova explosions of massive stars. A neutron star weighs about 1.5 times the mass of our sun, packed into a radius of only about 7 miles. It is so dense that 1 teaspoon of neutron star material weighs 10 million tons. Black holes are even more extreme. They weigh 10 or even more times the mass of our sun. The radius of their event horizon is about 20 miles, and the density of the singularity at the center of a black hole is infinite. To put this in perspective, here's a map of Boston. I am talking to you right now from the Center of Astrophysics in Cambridge, shown in the red arrow. So on this map, this is the area that a neutron star or a black hole would cover. They are about the size of a typical city. And remember, these objects weigh several times the mass of our sun. Now, to generate gravitational waves, it is not enough to have neutron stars and black holes. They have to exist in pairs that collide and merge. As amazing as it sounds, we actually know from our own Milky Way galaxy that such neutron star pairs exist, but they're incredibly rare. This means that if we want to detect gravitational waves from the mergers of neutron stars, we have to build a detector of gravitational waves sensitive enough to reach out well beyond the Milky Way into millions of other galaxies. Whether pairs of black holes exist in nature was actually an open question until recently, because being otherwise dark, there was no way for us to see them with traditional telescopes. But let's go back to the small strain of gravitational waves. So even for neutron stars and black holes colliding with each other, this is still an incredibly small change in length that we have to measure in order to detect the effect of gravitational waves. 1 part in 10 to the minus 21. What does this actually mean? Well, let me give you some analogies. This is equivalent to measuring the distance to the nearest star, which is about 25 trillion miles away, to a precision of the width of a human hair. It is also equivalent to the tallest mountain on Earth being the size of an atomic nucleus. Finally, it is equivalent to measuring the length of 4-kilometer steel tubes to 1 part in 1,000 the size of a proton. Now, I'm specifically making this last comparison because this is how we actually detect gravitational waves. Meet Ligo, the Laser Interferometer Gravitational Wave Observatory, which was conceived in the late 1960s. Ligo was funded in 1990, its construction ended in 2002, and it took initial data for a few years, but with no detections of gravitational waves. In 2008, the National Science Foundation decided to fund Advanced Ligo, an order of magnitude improvement in sensitivity, with the goal of making the first astrophysical detections of gravitational waves. The basic idea at the heart of LIGO is a laser interferometer. Essentially, it's an incredibly precise machine for measuring the length of 2 L-shaped arms for the purpose of sensing the compression and stretching effects of gravitational waves. A laser beam is sent into the 2 arms, which have precisely the same length, and then returns and cancels out. But when a gravitational wave passes through the detector, one arm and then the other are stretched and compressed, changing their length by 1,000th the size of a proton. And the laser beams therefore come back just a tiny bit out of phase. What LIGO does incredibly precisely is to look for these minute out-of-phase signals. There are, in fact, 2 identical LIGO detectors in the US, in Hanford, Washington, and Livingston, Louisiana. And the reason for that is to ensure that gravitational wave signals are real by correlating them across large geographical distance. Now, LIGO is not alone. It is part of a large and growing network that includes the operational Virgo detector in Italy, the COGRA detector under construction in Japan, and a planned clone of LIGO in India. This network is also designed to allow us to roughly locate the direction of gravitational wave sources through triangulation. So LIGO is designed to capture the final few seconds before merger of black hole and neutron star binaries and to measure the strain and frequency evolution of the gravitational waves. You can see how the strain, the amplitude of the signal, increases and the frequency increases as the two black holes approach each other in the final second of their life. And the signal then stops when the black holes merge. Note that the final speed of the black holes right before they collide and merge is about 1/2 the speed of light. This is absolutely incredible. This uptick in amplitude and frequency close to merger is called a chirp. It's a technical term that's used in the community. Okay, so now we're going to put Einstein, gravitational waves, and LIGO aside for a couple of minutes and switch gears from astrophysics to chemistry. Here I'm showing the periodic table of the elements, something that I'm sure all of you have seen at some point in your life. It is one of the triumphs of human imagination in terms of organizing and classifying nature. There are presently about 120 different elements known, but the periodic table organizes their properties and behavior in an incredible fashion. Now, this is how astronomers look at this amazing complexity. We have hydrogen, helium, and then everything else that we call metals. This is not a joke. This is how astronomers really look at the periodic table. But more seriously, astronomers are interested not only in the properties and classification of the elements, but in how these elements actually form in the universe. Specifically, what cosmic sites and processes are responsible for forging different elements. It was recognized in the early 20th century, partly through work here at Harvard, that hydrogen and helium formed primarily in the Big Bang. Light elements, such as carbon, nitrogen, and oxygen, form in the cores of stars like our own sun. Heavier elements, up to iron and cobalt and nickel, form in the cores and the supernova explosions of very massive stars. And then it was generally assumed that the heaviest elements in the periodic table, about half of the periodic table, also form in supernova explosions, because we had no other explanation. So at least that's what the textbooks all said as recently as 2016. Now, one thing the periodic table does not tell us is how abundant the various elements are in the universe or on Earth. For that, we have to look at a plot like this one, which shows the relative cosmic abundance of the various elements going from the lightest and most common, like hydrogen and helium, to the heaviest and rarest, including gold and platinum. These heavy elements have an abundance of less than 1 part per billion compared to hydrogen in the universe. So they're incredibly rare. The pathway for the formation of these heavy elements is something called R-process nucleosynthesis, the rapid process of element formation. Here, rapid means that in order to build up such heavy elements requires a large and rapid influx of neutrons into lighter seed nuclei before these neutrons have a chance to decay into protons and build up successively heavier elements. So the key question in my mind approaching this field was, where in the cosmos does the R process happen? Or equivalently, where does all the gold come from? So with this question in mind, let's now return to gravitational waves and LIGO. Advanced LIGO operations were scheduled to begin on September 18, 2015. But 4 days earlier, during the final hours of engineering shakedown, the unimaginable happened. LIGO detected an incredibly strong signal of gravitational wave, which you can see here in this image. You can see the final half a second in the life of a binary object colliding and merging. This was GW 150914, the gravitational wave event of September 14th, 2015. It is the first burst of gravitational waves ever detected by humanity. And it was the merger and collision of two black holes weighing 35 and 30 times the mass of our sun at a distance of 1.5 billion light years away from Earth, as shown in this computer simulation. So just like that, a century after the original prediction of gravitational waves, 30 years after work on Ligo began, and after spending $600 million on building Ligo, a gravitational wave event was finally detected, and the leaders of the Ligo experiment won the 2017 Nobel Prize in Physics. But to me, watching the Nobel ceremony, despite all the excitement, the more pressing and lingering question still was, so where in the cosmos did the gold in the Nobel Prize medal come from? And for this, we have to shift our attention away from the mergers of black holes to the collisions of neutron stars. When two black holes collide, they simply merge to form a more massive black hole. But when neutron stars collide, we think that much more exciting things happen, as shown in this computer simulation of the few milliseconds before, during, and after the collision. This violent collision leads to the ejection of neutron star material away from the system at speeds of up to 1/3 the speed of light. And in this ejected debris, which is rich in neutrons because it comes from neutron stars, we can imagine our process nucleosynthesis, which requires a lot of neutrons, taking place. We can look at this movie and imagine gold being forged in this material. But how can we detect and demonstrate the signature of our process nucleosynthesis, of gold formation? Luckily, some of these R process isotopes and nuclei are unstable, and their radioactive decay can power a flash of visible and infrared light, lasting about 1 week, and with characteristics, with spectral characteristic wiggles, unlike any other astronomical event. So these two plots show how the brightness of such an event powered by the radioactive decay of these R process nuclei will evolve over time, and what the spectral properties, the brightness as a function of wavelength, would look like. So these are theoretical expectations. So this was our game plan starting in 2015 when Advanced LIGO turned on. We were waiting for LIGO to detect gravitational waves from a neutron star collision and then alert us to that event. We then planned to use special instruments to scan the sky region where the gravitational waves came from for a visible light counterpart. And then, if we could detect that counterpart, we will take over every big telescope around the world and in space to search for these signatures of the R process, of the formation of gold. So here we finally arrive at August 17th, 2017. It is 9:20 a.m. in the morning Eastern time, and I'm sitting in my office in the midst of a thrilling committee meeting on graduate level curriculum revisions when my cell phone goes off. Now, being polite and considerate, I ignore my cell phone, and then my office phone starts ringing, and then I get a blast of text messages. So I understood that something big was going on. So I kicked everyone out of my office, and I started checking my text and my email and my voicemail, and the message was, LIGO and Virgo detected a neutron star collision. And here it is, the chirp signal of GW 170817, the gravitational wave event of August 17th, 2017, the first neutron star collision ever detected. So it was time to activate our game plan. So it's 9:21 in the morning, Eastern time. We know that a neutron star collision was detected. We know from the gravitational wave signal that the event is located about 125 million light years away from Earth, to a region that is about 100 times the size of the full moon, shown in this image by these white ellipses. And we know that the region will be viewable first from Chile 10 hours later. So after a full day of planning, spending those 10 hours working through all the possibilities, working through our game plan, it is now finally 7:13 p.m. in the evening. The sun finally sets in Chile. We open the telescope dome and we begin to take images, each image shown schematically here as a red region. And every image that comes off the telescope is inspected to search for a new source of light. Now, at this point, the tension was just unbearable. Will we be able to locate the visible light from the first neutron star collision ever seen? That question was just going through our mind nonstop. And then an email pops up from my colleague, Ryan Chornock, who was poring over some of the images at his home in Ohio. And he says, check out NGC 4993. This is just the name of a galaxy in the sky region of this gravitational wave event. Attached is our image and an archival pre-existing image of that region of the sky. And he also says the galaxy is located at a distance of 40 megaparsecs. That's 125 million light years, exactly the same distance as the neutron star collision. And so here I will show you the image that he attached to this email. So you can see on the left side our discovery image, and on the right side, a pre-existing archival image of that same galaxy. And to make sure that we didn't miss the source in all the excitement, he put a bright red circle around this new source of light that was not there before. Now, it's hard for me to put into words exactly what I felt. I remember being just stunned. This is the first time that we have seen light associated with a gravitational wave event. It really felt like a historic moment. But there was little time for reflection. We had to proceed to the next step of our plan of action. So we continued observing this source every single night, tracking it until it faded away to obscurity, as you can see in this time-lapse movie. You can see the source bright initially, and then slowly fading away over the period of about 10 days. In fact, this was so exciting that we rapidly repointed the Hubble Space Telescope to this source. And we saw this amazing image of the visible counterpart of GW 170817 in the context of its beautiful host galaxy. So after nearly a month of effort, we collected data all the way from ultraviolet to infrared wavelengths, using 45 different telescopes around the world and in space. This is by far the largest collection of telescopes ever pointed at any single astronomical event in such a short period of time. You can see in this plot how the ultraviolet light, shown in blue colors, faded away very quickly within about 2 days. The visible light, shown in green and yellow colors, faded away after about 10 days. And the infrared light, shown in red, lasted about a month. Now, here to remind you is again a comparison to the theoretical models for light produced by the radioactive decay of heavy elements. This is a remarkable agreement between what was predicted and what we saw from this event. Now, we studied not only the brightness of the source, we also collected spectra, brightness as a function of wavelength. You can see how the source fades away and develops these characteristic wiggles that serve as the fingerprints of heavy elements. And here again is a comparison to the pre-existing theoretical models. Once again, you can see a remarkable agreement between the location and shape of these undulations in the spectra. So with all of this information, you can say that we literally found the pot of gold at the end of the rainbow. We finally had definitive direct evidence for the formation of heavy elements, including gold, in an astronomical collision of two neutron stars. So after 2 months of intense observations and analysis, after writing 10 scientific publications in 2 months explaining all the properties of this event, finally on October 16th, 2017, we announced the result of our study at a joint National Science Foundation and NASA press conference in Washington, D.C. And you can see a picture of me from that press conference explaining the results of our study. And this was incredibly exciting and very rewarding to share this information. Now, once it was announced, the story was reported all over the media. And what I found most fascinating is that business journals, which generally do not report about science, were all fascinated by this particular story. I wonder why. So now to answer the question that I know is on everybody's mind. So how much gold are we talking about? How much gold did this collision actually produce? Well, imagine the Earth was made of pure gold. The total amount of gold produced in this one neutron star collision was 10 times the mass of the Earth. How much is that worth? I actually checked earlier today, and at today's market rate, this is the equivalent of about 3,000 octillion dollars. That's 3 with 30 zeros after it. But before any of you rush out of the door to start prospecting for this gold, just remember that it is all located in another galaxy 125 million light years away. But more importantly to me than any imaginary monetary gain from this gold is that we actually ended up rewriting the astronomer's periodic table. This is what shows up on Wikipedia now. The origin of these heavy elements is merging neutron stars. And now it's official. So what's next in this area of research? Ligo and Virgo have so far detected more than 30 black hole collisions and one additional neutron star collision to the one that I showed you. By next summer, they will reach their design goal of being able to detect these binary neutron star collisions to a distance of about 600 million light years. That's about 5 times further away than the event that I described to you. The Kagra detector is now finally operational, and we expect that Ligo, India will become operational later this decade. And the next generation detectors are already being planned to be built on the ground and in space in the 2030s and beyond, with this incredibly ambitious goal of detecting every black hole collision in the history of the universe, and as many as 100 neutron star collisions every single day. This is going to completely revolutionize the study of the universe in a new way that is not accessible to us today. So I want to end this talk with a few parting thoughts for you to reflect on as you keep thinking about this topic. First, after millennia of studying the universe with just light, first with the naked eye and now with telescopes, we now possess a completely new way of exploring an otherwise invisible universe. Second, a journey that began with Einstein in 1916 has led us in a completely unexpected direction, tying together gravitational waves, light, and the origin of the heavy elements. To me, this is really the beauty of science and serendipity in science. And finally, a similar neutron star collision in our own Milky Way more than 5 billion years ago seeded the gas from which our solar system formed with gold that eventually ended up in your jewelry. So to paraphrase Carl Sagan, who said, "We are all star stuff," I would add, our jewelry is colliding star stuff. Thank you very much for joining me this evening, and I will now be happy to answer any questions you have.
Thank you, Edo. That was fascinating. Sounds like we need to target this galaxy and head on over there. So we're now ready for the Q&A portion of our lecture. I did see some questions coming in from the audience, so I wanted to start pulling those up. Let me begin with one that popped up earlier. From Kurt on YouTube, can you describe the measurement uncertainties and statistical confidence for these findings?
Yeah, that's a very, very good question. And so our uncertainty in the amount of gold that was produced is about 20%. So when I said that the amount is about 10 times the mass of the Earth, it's plus or minus 2 times the mass of the Earth. But the confidence in the finding itself is very high. In fact, the great thing about all of this data is that we have made it all public. And there are multiple groups of astronomers around the world that have used these data, as well as some of their own measurements, to carry out independent analysis of these and essentially reach the same conclusion.
Okay. Thank you for your question, Kurt. Let me go ahead and select another one on YouTube again. Why is so much more gold formed in neutron star collisions versus supernova? Is it just the sheer quantity of neutrons?
So that is an excellent question. So I would say that from the evidence we have now, the only place in the universe where we actually see evidence for the formation of gold in these heavy elements is neutron star collisions. It is not clear that supernova explosions actually contribute at all to the formation of those elements. We know that they produce somewhat lighter elements like iron and nickel and cobalt, but we do not have any direct observational evidence for the formation of gold in supernova explosions. So it is possible that they produce some of it, but we're going to have to wait for evidence for that. The thing that we're going to do going forward is, as we find more of these neutron star collisions and we measure the amount of these heavy elements that's produced in each collision, we can essentially build up an inventory of how much of this material is being produced and compare it to how much of this material is known to exist in the Milky Way. And if the two add up to the same number, then that means that neutron star collisions really are the dominant place in the universe for formation of heavy elements.
Okay, let's go ahead and go to the next question. From Stephen on Facebook, are gravitational waves omnidirectional?
They are. They are omnidirectional. They are emitted by these sources in all directions, which means that we can see these sources, we can detect them in gravitational waves, regardless of how this binary system is oriented relative to Earth. So it could we could be viewing it face on, or we could be viewing it edge on, and we can still detect gravitational waves.
Okay. And I actually had a personal question that just popped into my head. So it sounds like after August 17th, 2017, you worked with a lot of astronomers and observatories around the world to target that one source of light. So what was collaboration like? It sounds like you just told everyone to stop everything, target this one source. How hard was that to implement?
So I think it was challenging and it was fun, and I think that people enjoyed being part of this process. But I would say that because we had this idea that we wanted to do this in advance of when the event actually happened, we actually already secured telescope time in advance with the understanding that we might have to, kick somebody off the telescope and repoint it somewhere else. Eventually, we actually included all of these people, all of these astronomers that helped us at the telescope to collect data, that stopped what they were doing and collected data for us. All of them were included as authors on our publications, and that was one way of paying back and giving them credit.
Okay, that makes sense. Okay, let me see. I'm noticing some more questions came in from the audience, from Meredith on YouTube, from her 9-year-old son, John. What are the largest objects LIGO has detected colliding?
So that's an excellent question. The largest objects that LIGO has detected so far is the collision of 2 black holes, each one weighing about 60 or 65 times the mass of our sun. And in fact, these black holes were so massive that we still don't have a good theory for how they formed. They are much more massive than what we anticipated black holes could be.
Wow. Okay, we do have some more questions still from Jack. What type of future work with LIGO is ongoing or anticipated to this related research or study?
Yeah, so LIGO is currently offline for upgrades. And so the way they've been running the experiment over the last few years is to operate it for scientific observations for a few months to a year, then have downtime for about a period of a year and a half for upgrades, until they reach their design goal, which they're planning to do by next summer. So when LIGO turns on in summer of 2022, we anticipate that the rate of detections will go up significantly. We are anticipating detecting several black hole collisions every week, and maybe one neutron star collision every month. And so that will be the primary operational mode of LIGO, is collecting data and finding more and more of these gravitational waves, building up our understanding of these systems. At the same time, there are additional upgrades to LIGO that are being planned. So there is a good chance that it will be taken offline again, and the sensitivity of the detectors will be increased by another factor of 2 or 3 better. And that will, of course, open up a larger volume of the universe for detections of these gravitational waves. And then the hope is that sometime in the next decade, we will start building a new set of gravitational wave detectors that, instead of having these 4-kilometer arms, will have 40-kilometer arms. And those will be 10 times more sensitive and will essentially be able to see every black hole collision in the entire history of the universe.
So will you continue studying this one original source that you found, or are you done with that particular?
Yeah, that's an excellent question. Believe it or not, we are still observing that source, not in visible light or in infrared light, but in radio waves and X-rays. So in those 2 parts of the electromagnetic spectrum, we are still able to detect this source slowly fading away. Even now, 4 years later, after it happened, we just published a paper about 2 weeks ago on new detections in X-rays from this very same source. So these sources contain an enormous amount of information, and we're trying to squeeze every little bit out of it.
Okay, thanks for your question, Jack. Let me get to some more. From Arthur, is space mining within our solar system a realistic expectation from economists?
I'm not sure that that's a good question for me as an astronomer. Scientists are not known to be good with money. But I think it's an interesting idea, and there are in fact people here at the Center for Astrophysics and in other places who've been studying the feasibility of actually being able to mine asteroids or mine the moon. And I think right now it's mainly a question of, is it feasible from an engineering perspective, from a scientific perspective? Eventually, the question of the economics of it is going to have to be tackled, because it's expensive to send mining craft to space and to land on an asteroid and mine it.
Okay. Let me go ahead and pick the next one from Stephen. Hypothetical question. Could gravitational waves bounce or reflect off the cosmic microwave background?
That's a very interesting question. I don't think they can reflect or bounce from the cosmic microwave background. But interestingly enough, the cosmic microwave background radiation itself might encode gravitational waves that were produced right after the Big Bang during a period called inflation. And this is something that people are actually looking for, this signature of gravitational waves from the early universe encoded in the cosmic microwave background. So this is something very different. This is not gravitational waves produced by the collision of objects that I just described in this talk. This is gravitational waves produced from just the inhomogeneity of the universe as it was rapidly expanding during inflation in the fraction of a second after the Big Bang. So this is an active area of investigation. We have not yet definitively seen that signature.
Okay, thank you. Next question from Rick on YouTube. Does this mean there is a nearby neutron star to Earth?
So there was a nearby neutron star to where the solar system formed 5 billion years ago, before the solar system formed. And that neutron star collision produced these heavy elements that got incorporated into the solar system, into the sun, into the Earth, that we now dig outside of the Earth. So when we go and dig for gold, it's gold that was produced by a neutron star collision somewhere in the vicinity of where the sun formed. Now, that happened a long time ago, and that aftermath of that collision was a black hole that is somewhere, floating around in the Milky Way. But there are neutron star binaries in the Milky Way. None of them are particularly close to where the Earth is, And some of them will merge within a few tens of millions of years from now. So, some future generation will actually get to see this process, not in some galaxy far, far away, but in the Milky Way itself.
Okay, thanks for your question, Rick. Next one from Kurt. What is the smallest scale event expected to be detected after all planned LIGO upgrades?
So if I understand the question here, the smallest scale means the closest to us. So we could find these neutron star collisions even closer than the one we found. But just to put it in perspective, in a galaxy like the Milky Way, a neutron star collision happens once every several million years. So it's going to be a while before we see one in our own galaxy, and it's going to be a while before we see one in, for example, the Andromeda galaxy, which is our nearest large neighbor. So it's just a question of statistics. The reason we find these events at large distances is because there are a lot of galaxies out there at these very large distances, millions of galaxies. And so once in a while, one of those galaxies will produce one of those collisions. And so even as we make LIGO more and more sensitive, the chance of finding one of these very nearby is still very, very low. It's a 1 in a million year chance in the Milky Way.
Okay. Thank you for your question, Kurt. Question from John on YouTube. Have there been any multi-messenger events detected that produce gravitational wave plus light plus neutrinos, I think?
Yes, so excellent question. And so far we have not seen a single event that produced all three. So we have seen the event that I described, which produced gravitational waves and light. And we have seen the famous supernova 1987A that happened in the Large Magellanic Cloud. That one was detected in light, like every supernova, but also detected with neutrinos. So far, we've only gotten 2 out of the 3 for these 2 events. There are just these 2 events, one in 1987, one in 2017, that have produced more than one form of signal. The hope is that as these neutrino detectors also improve in their sensitivity and the gravitational wave detectors improve in sensitivity, that eventually we might be able to see all 3 of these from one astronomical event, and that will be amazing.
Okay, thanks, John. Next question from Jim. How would it be possible to detect all black hole collisions in the history of the universe? Wouldn't the signals of some already passed the Earth and some not arrived yet?
Yeah, so what I mean by detecting every black hole collision in the history of the universe, it means detecting every single one when our detector is active. So for example, if we build it in 2030 and it works until 2060, then during those 30 years, we will detect every black hole merger or every black hole collision whose signal arrived on Earth in that time period. So of course, some of these collisions have already happened. That signal has already passed through Earth, 10 years ago or 100 years ago or 1 billion years ago. And some will happen in the future. But during the time when this experiment runs, we will be able to detect all these black hole collisions, regardless of how far away they are from Earth, as long as their signal arrives on Earth at the right time.
Okay. Let's see. A question on Facebook from James. Is there a more active observed location?
So what I take this to mean is there a specific part of the sky or a specific part of the universe is particularly active in producing these gravitational wave events? The answer is no, at least as far as we can tell so far. These events come from all random directions at all times of day, from all kinds of galaxies. And the reason is that on these very large scales that we're looking at, the universe is incredibly uniform and incredibly homogeneous. And so we don't necessarily expect that one side of the universe or one part of the universe or one collection of galaxies will be more active in producing gravitational wave events than others.
Okay, next question from YouTube. Was the neutron star collision actually happening when you saw it happening, or did it happen far before?
Excellent question. So thanks to the magic of the speed of light being not being infinite. The event that we saw on August 17th, 2017 actually happened 125 million years ago. So hence the distance of 125 million light years. So it happened a long time ago, and that signal traveled to us for 125 million light years and arrived just at the right time on August 17th when we were ready to detect it and study it.
Interesting. Okay. So next question from Kat on Facebook. What advice would you give to a young person interested in studying astronomy?
That's an excellent question. And I have to say that my interest in astronomy started as a young person when I was 12 or 13 years old. And my advice would be to nurture that curiosity. There's a lot of really interesting literature, a lot of really interesting questions. There are a lot of opportunities for young people, in high school to get actually involved in research. We have programs here at the Center for Astrophysics that involve high school students in research. And so I think that's a great opportunity to get involved and kind of get a sense and a taste for what astronomy is like and see if you like it. I know that for me, when I went to college and I started studying astronomy, I knew I loved it as a principle, but I became really hooked. Once I started kind of understanding the subtleties and the interesting questions and getting more into the physics and math and using telescopes. I mean, it's amazing to go to observatories all over the world in all these remote places and use telescopes. So I think just gaining as much of that experience as possible would be a great way of seeing if that passion really lasts.
Okay, thanks for your question, Kat. Next question from Yanni. Hopefully I'm saying that name right. Is there a specific era in which more neutron star collisions occurred?
So that's an excellent question. So when we look at the universe as a whole, one of the things we've learned over the past 10 or 20 years is that earlier in the history of the universe, the universe and galaxies were more active in forming stars, much more so than the universe in its present day. So we're kind of in a declining phase of new stars being formed in the universe. So about 10 billion years ago, so the age of the universe is about 13.5 billion years. And so about 10 billion years ago was kind of the peak of that activity of stars being formed. And we expect that there were more stars and more of these massive stars and more of these neutron stars and black holes being formed and more of these collisions happening. So a lot more of them happened earlier in the history of the universe compared to today. Now, of course, this process of these two neutron stars forming and then eventually colliding, that whole process takes a long time. So one thing I did not mention is that, this collision happened 125 million years ago, but that system of two neutron stars actually formed 11 billion years ago. And it spent those first 11 billion years slowly spiraling into each other until that collision eventually happened. So even though the system formed a long time ago, it took it a very long time to reach that point of collision.
Okay, thank you. I actually had a personal question before we get to this next question from Rick. So there's all this gold floating in space. So are there any rules about who that technically belongs to if someone ever goes out and tries to get it, or how does that work?
So that gold that's out there, a lot of it is incorporated in astronomical objects, in stars and planets that are out there, including our own solar system. Some of it is mixed in with the gas that's between stars, what we call the interstellar medium. And that gas is incredibly dilute. You would have to cover a vast volume of space to just find one atom of gold. So I'm not sure so there are no regulations on any of this, but I'm not sure that it's a particularly profitable direction. Asteroid mining might be more profitable, but even there, I don't know what the legalities are.
Okay, thank you. All right, back to Rick's question on Facebook. As there are more gravitational wave detectors, will increased directionality help us find the signals in other wavelengths?
Yes, so that is definitely something we're looking forward to. So when we only have 2 or 3 detectors, which is the current situation, these locations on the sky from where the gravitational waves come from are quite large, and it's very challenging to scan such large areas on the sky very quickly to find that light signal. We were able to do it with that particular event that I talked about, but it's not obvious that we will be able to do that every single time. As more detectors come online and they are located further apart, so right now our longest baseline between detectors is between the US and Europe. With the detectors in Japan and India, we will have longer baselines. That means we could triangulate the signal more accurately to a smaller patch of sky. And that means that we will have a much easier time using a broader range of telescopes to be able to pinpoint that the light signal that's associated with the gravitational waves.
Okay, thanks for your question, Rick. Let me go through the other ones. From Ron on YouTube, what happens when the gravitational waves from two distinct events intersect?
That's a good question. So remember that gravitational waves are kind of a compression and squeezing of space-time. So this compression and squeezing will happen almost irrespective of the two events happening, kind of passing through the same point in space. They do not really interact with each other.
Okay, we have time for, I think, one more question. We're nearing 8 o'clock. So let me go ahead and bring it up. Okay, last question from Catherine. What sparked your interest in gravitational waves as a field of study?
Yeah, that's a really good question. So, my interest in this particular field was kind of threefold. One was this question of the origin of these very heavy elements and the notion that they might come from neutron star collisions, and that the way to find these neutron star collisions predominantly is through gravitational waves. So that was one part of it. The other one is that one thing I've always loved about astronomy is that it's very much driven by at least my passion for it is driven by discovering new things. And it was clear that with this new capability of studying the universe in a completely new way that we've never had before, that was certain to lead to very interesting discoveries. And that definitely excites me on a personal level and what drew me to this. But another aspect is that I actually did my dissertation work back in 2000, between 2000 and 2004, on objects called gamma ray bursts. And it turns out that, and that was kind of part of the results of my work, is that we think these gamma ray bursts are also caused by neutron star collisions, just ones that are much further away that we cannot yet detect in gravitational waves. And so I was also interested in the question of how do I definitively prove that that's true? And the way to do it was to detect one of these neutron star collisions nearby through gravitational waves and see if the signatures that we see in the electromagnetic radiation are similar to the ones we see in these gamma ray bursts. And it turns out from this event that in reality, that's actually what happened. So we now have this direct link between gamma ray bursts and neutron star collisions as well. So I kind of feel, as part of my thesis work, I kind of feel vindicated that finally we've been able to show this definitively.
That's so exciting. Well, this concludes Observatory Night. So thank you so much, Edo, for joining us. And thank you, everyone, for tuning in and asking so many amazing questions. So before we end, I wanted to encourage everyone to consider supporting the Center for Astrophysics and consider giving at the link that's going to appear on your screens now and in the comments section. Any amount will help support the important research and engineering that happens here at the Center for Astrophysics every day and the effort to answer humanity's greatest unresolved questions about the nature of the universe. We look forward to seeing you again for our next Observatory Night, which will be announced at a later date on our social media channels. Visit our website, cfa.harvard.edu, for more information about the Center for Astrophysics and Edo. Thank you and good night, everyone.